All right, so that's the most controversial thing I've ever said in my life. Please don't repeat it. Cool. So checking this out. I don't have a calculator to screencast to you guys, but when you hit the summation button, your calculator says, okay, what? And this is what should be on your screen right now. Okay, we're going to type in this mess. So it's going to be ugly, and I know I wish that it did the pretty print while you were typing it in, but let's make sure we can sort this out. We have e to the power of -1 plus 4 over 10, and now we need to make a decision. I is the index that we use when we write them. That's pretty common and normal. What's a more natural choice for that when we're typing onto a calculator? X is probably what I would use. So I'm going to use X in place of I when I'm typing this in. Now you could use I as well, I think, but we're just going to commit to X in case our calculator represents what we're doing as an imaginary number. So we'll close our parentheses, and we have to add the other one. The parentheses here are the hardest part. Remember that anytime you have a left parenthesis, just make sure you have a right parenthesis to go with it. So here's our first expression. The second one is e to the power of 1 minus 4/10 x again. And then here's the part where we probably didn't have. If you guys got a text from Isha because she asked about this at the end of Chess Club on Friday, you might have seen it. But if not, that's also okay. We're taking the sum, and notice we've never said any of the other stuff. What normally goes on the sum before we plug in all this mess? We say the sum what? From I equals 1 to n. This time, it's not I, it's what? X. And it goes from where? 1 to 10. If we have this, and I know it's ugly to type in, but don't keep it secret when you type this in and get an answer. Let me know what you guys get when you evaluate this summation. We're almost right. Yours says what? C-O-S-H? Interesting. Try it again, do diamond enter. So what we've just stumbled into is the hyperbolic cosine, which apparently relates to these powers of E. Okay, 65.23. There's only one thing left. Is there anything that I've missed here?
Wait, I think I did. Someone second.
Okay, what did I leave off? There's one thing that's going to skew our answer wildly. 4/10. So with this, I can include it in the summation if you want. Just simply type times 4/10, and it's going to say answer times 4/10. Hit diamond enter so it doesn't take you back to hyperbolic cosine stuff, and let me know what you get. I'm going to sneak my 4/10 here, and you're going to say it's approximately. Say it again. 26.094. Hey, that's exactly what the textbook has. If I wanted now to do the part B of this, and we're just going to knock it out real quick, do we have to redo everything that we've done? What's the only thing that's going to change? This is going to change from a 10 to a 50. This will change from a 10 to a 50. This will change, and this will change. I want you guys to simply go in and change anywhere there's a 10, change it to a 50 in the previous line. You can backspace on your calculator, and I want you to approximate if we use 50 of these. I need my notes because I have no idea where we're going from here. Once you get a number, remember diamond enter, shout it out. Let's see if we can get a second and a third. Can you repeat that again? So this one does have pretty print, and I forgot that I had this. Plus e to the if it says busy, it's just thinking. Like this one, I'll take a minute to think about it as well. Here's me multiplying by 450. Whoa, dang it. This thing times 450 is 23.0800 is what this calculator comes up with. Do we get the same answers? Awesome. So we see that with 10 rectangles, our approximation is like 26. With 50, our approximation is 23.0800 or 01, if you will. What's going to happen if we change it to 100? Do you think we're still overestimating or are we underestimating? Because we certainly overestimated on the first one because we lost 3 units of area when we added this many more rectangles. I bet we're overestimating again, and that's just a hunch. And all we have to do to change this, I'm just going to take everything that has a 50, and we're using how many instead? 100. So I'm going to delete the 50, and I'm going to insert. So insert. So 100x and 100x. When we do it with 100, I'm just recalculating it just so you guys can get a verification. On this calculator, I get a wonderful 22.73. Do you guys get the same number? Now, I want to really stress this. The other day in class, you guys did awesome. And I know that we were doing maybe a bit more than we needed to, and that's okay. Everything that I was seeing on the board was stellar stuff that we are ultimately going to use. We just might have gone a little bit further than we needed to on that one particular problem. My bad for giving you guys such a terribly long homework assignment the other day. Cool. Should we do one more like this, or do we feel comfortable and okay with using the calculators? One more. We're not going to do like another 3 parts. I'm okay with any of these. We're going to knock out one more, and we're just going to do it with 100 rectangles. But are we going to do... And whoa, I'm all goofed up here. What am I doing? Here we go. Okay, that was 48, right? There we go. Which of these other ones do we want to do? We can do 47, 48, or 49. Or 50. Just kidding. 47, 49, or 50. Can we do all of them? No, we can't do all of them, but thanks for asking. Cool, let's do number 50 for 100 rectangles. Number 50, 100 rectangles. I'm going to give you guys a minute. Do you want to do it in your notes, or do you want to go up to the board and knock them out? Find a spot on the board. Teams of 3. Get 2 of your peers.
3.
Teams of 3. I'm going to give you guys a second. I will write this problem up on the big board so we can see it. And actually, I'll just freeze it. Mr. Baker, do you want to know what I've been complaining about for years? That when I want to work a problem, when they're working a problem and I want to work a problem, I can't do it. I didn't know you could freeze the screen.
Oh, yeah.
By coincidence.
Yeah, freeze.
There's a group behind. Pick your 3. I don't care who
What
you're
has to
with.
be 4?
We're
One
gonna
group
kill
came
it.
before this time.
Just kill it. We're gonna kill it.
I'm always fine. It wasn't all fine, but you tricked it, no,
Yeah, no, that's
Yeah.
super helpful.
Alright, which one are we doing?
Remember, the writer
50?
cannot speak. You have to communicate your ideas.
Wait, what page is it?
Hey, well, what page is it?
Erase it right now.
50 or 403. Should I pause the recording?
Sure, that'd be great. it has been all limits all the time. And here pretty quickly, we're going to start learning some very convenient shortcuts for us. So we will just continue on with where we left off last class. We did several examples. Harder or easier than derivatives, just out of curiosity? It's more commonly thought of as harder, but you guys are doing really well, and keep it up. So we are still in 5.2, and this would technically be 5.2.2. Last class on Friday, we just worked through examples, right? Up at the board, we checked the homework, we went through a few of them. We spent a lot of time doing that one the other day. I guess it was 48, but we just did the same thing with number 50. So for today, I lost my notes the other day. What was our main bullet point that we started with in 5.2? So definite integrals, and then we said, like, here's the Riemann definition for the Riemann, or the definition for the Riemann integral. And then we just did examples. Is that correct? Okay. So moving on from there, we're still in the same section. We're just going to finish it up. What we're going to focus on today are the conditions that we need for the existence of an integral. So conditions. Anybody remember the existence? Is there a shorthand for exists? That's a good point. That screen's also frozen, so let me get that one thawed out a little. Meter Y. You guys look insane. I meant to bring the bubble stuff today, just so you guys know. Hey, thanks, get red. Baller. Nope. There we go. Okay, we're looking for conditions for the existence of the integral. And I'm just going to use existence with a backward capital E. Conditions for the existence of the integral. Okay. Now, while we're looking at these things, it turns out that maybe what is intuitive to us is not really all that's there. So normally, we typically write the following. Normally, if we wanted the integral, like I'm going to write this out a little bit. If I want the integral, what do I put for the, like just in general, for the lower and upper limit of integration? What have we been using? A to B. And then in here we'd have some function. And I'm going to throw you a curveball here real quick. I know it's going to look a little bit different. Let's say it's f of alpha. Hypothetically. We used alpha. What goes out here? D alpha. Our variable of integration matches the variable that we use to define the function. If this had been f of beta, it'd be d beta. Or f of theta, it would end with d theta. They stay consistent. Okay, normally we work this out where alpha, or A rather, is less than or equal to B, because we have the lower limit and the upper limit. Now, it turns out that everything that we've had, all of this is true, and it does exist, and it happens, but this is just convenient. It is only convenient. And it turns out that when we're thinking about the integral, maybe there are some other situations that we would want a better way to write an integral out. So what we're about to get right now in conditions for the existence of the integral is really just code word for some properties that we're going to get with the integrals that take this idea and say, what if it weren't always A is smaller than B? Cool. So we get a few common properties that we're going to deal with. Now, each of these properties, I'm going to change colors in between only so we can distinguish them easily. So let's check it out. The first one, we're going to go back and forth just so you know. I am going to be real solid with 15 seconds. We're just going to alternate. If you're talking with, or whoever you're next to, we'll say person nearest me starts chatting initially. Second question, you're going to just switch whoever speaks. We'll do 15 seconds to talk it out with our groups, or you'll explain what you think is happening with your neighbor, and then we'll come back together, over and over, alternating back and forth who speaks. So here we go. Let's say that we have a function, and I'm just going to say that the function is defined. What do you guys think is going to happen? And we might have already addressed this. If I go a to a for some function, f of x. So I'm going to put an equal sign here. You shouldn't, but this is the question that we're working on. The integral from a to a of some function f of x. What do you think it is going to be when we evaluate it? Person nearest me, you're the speaker for the next 15 seconds. Go with your gut. Just what do you think happens here? 15 seconds starting right now. Okay, Rafa, I think I liked what you were saying. We'll go 30 seconds on the next one, just so you know, because that seems really quick. Rafa, you had a gut feeling right off the bat. What did you notice about A to A? We have how much delta x here? So no matter how many rectangles you try to cut it into, in the end, what do we multiply it by? So what's your gut about this integral? Hey, it's 0. If you try to integrate from A to A, you're finding rectangles, infinitely many of them, with literal width 0, not like approaching 0. This is 0 every time. And it doesn't matter how ugly and awful the function is. If I give you the worst possible function I can think of and I go from negative e to negative e, nothing to do. It's just 0. We're done. Keep an eye out for this. You will use it inevitably. Okay. This one gets strange. And this time I'm going to change the rules a little bit because I didn't like how that last one worked. 30 seconds. I'm going to give you guys to chat. Everybody can talk. I want you guys to see if we have intuitive thoughts on this. If I wanted, gross. I don't even know how to do this one. I got it. What if I did the integral from b, sure, b to a of f of x dx? Does this one feel strange to you? It should. Cool. I want your gut feeling on this one. Same thing, equals 30 seconds. Don't care if you're wrong. It's okay. I just want to see, what do you think might happen here? So I've got 30 seconds. Go. Anybody proud of your thought on this? Baker, what do you think happens with this?
I think it's the negative integral of a to b.
Negative the integral from a to b of f of x dx. Hey, he's absolutely right. It turns out that if we flop our bounds in this order, all that we see happen is it's the same as the original, just the opposite sign. Now, conceptually, this is a super weird idea, and we will certainly deal with it. We're going to get an area that's negative. Now, if every single problem that we've been working with so far, and we'll see this again, I assure you, but every problem, when I say find the area, is between the curve and the x-axis, right? Like, that's what we just always work with the assumption. Every single function that we've worked with thus far has been somewhere up here, and we're finding this area. And we found a bunch of positive areas so far. What if, and this one I think we'll see again, but is it possible that a function does this instead, and I want the area from here to here? Where does it live? If I were to draw the area between the curve and the x-axis. Below the x-axis, or I liked your word. One of you two. A negative region? Here's what negative area is interpreted as within our field here. Okay, so it doesn't really matter where it is. We see that something wonky happens when we switch the bounds and the order goes the wrong direction. Okay, so hit it.
Why did the integral just switch from A to B?
So love that question. Don't know that you're going to love my answer. We can prove that this works. But I don't like, and I just like, and I know it's strange. I don't have a better answer than because, unless you want to go through the proof, which I'm going to be honest, off the top of my head, I have no idea how we approach this proof because I'm super rusty with this. We can dig through an analysis text at lunchtime if you stop by. I got you. I hate the answer is because, but it's because.
So you can just do that.
So when you say you can just do that, maybe. Like what I'm like, just to show this exemplified, let's say we want to go from 6 to, I don't know, 7 of f of x equals. Now, if I wanted this to just be another integral, I can simply change a sign, and what do you think I should run from? 7 to 6. And this property is true, and it does work. It drives me crazy I don't have dx there. If the bounds switch, so does the sign. Okay. All right. Now, from these two properties, realistically, we get essentially everything we need. We're going to get 3 really quick theorems with these. So we'll go back to this dark blue color, and we're going to get 3 theorems that aren't going to be big if then. I mean, they are going to be if then, but they're not going to be crazy. So 3 quick theorems, and then we'll start doing some of these guys. So theorem, first of all, if f of x is continuous on the closed interval from a to b, which if you wanted to draw this, when we think about continuity with regard to drawing it, it means we don't ever have to do what? Somebody said it. I heard it whispered. It was one of you two. I don't know which one it was. Rafa, what did you whisper? Because I'm pretty sure I heard the word pencil. Weird. I'm going crazy then. What does it mean to be continuous? You never have to pick up your pencil. Somebody said it. I'm almost sure of it. But what about the calci version? Show me continuity with your hands. Hey, I like what we're all doing here. Why are you pointing at your heads? Half you are simping, the other half are pointing at your heads, but we're doing the same thing. Hold on. Yeah, right? Like, right? That was a couple years ago, but it still exists. Okay. So whether it's here or here, walk me through the calculus idea that we're highlighting. What is this part? So this just shows me what exists. The limit. This shows me not only does the limit exist, but the function is also equal to the limit at that point. So we have that idea of continuity. If I can draw the curve, you think I can shade the region between it and the x-axis? Like if I can draw it, certainly I can. And if I can draw that region, we could calculate the area, right? Which means if it is continuous and we wanted to calculate the area, then what also exists? What calculates the area under a curve? What's the name of this section? Louder. The integral must exist. It has to. I don't like that integrand. Integral from a to b of f of x dx. It exists. Guaranteed. You give me a continuous function, the integral will exist. Okay. Another quick one. And legitimately, I think today we're going to get these 3 theorems listed, and then not probably. Tomorrow we're going to have a bunch of time to work on stuff because I'm not going to have time to give you homework. Okay, the second one. If f has finite discontinuities. If f of x has, and I'm going to change that language, removable, or I'm trying to think of how we can word it. If I say finite discontinuity, do you guys think you grasp what I'm saying? It can have a hole, or it can just can't shoot up to infinity. We can't have an asymptote. Can I say finite discontinuities? Because way fewer words if we use that. If f of x has finite discontinuities, which just means we never shoot up to infinity, discos, then the integral exists. Now, that one's a little bit weirder, and just to convince you that this is reasonable and is intuitive, if I have something that has a discontinuity, something like, and I'm just going to go from A here to B, and let's say it's here. Can we still find the area underneath this curve? I mean, it's kind of ugly, but it'd be like this trapezoid added to this rectangle, and we can still do it, right? It's okay if it has discontinuity. What's the issue if it does this? Sorry. Why isn't that one allowed? It goes to infinity. So when I try to calculate the area, if it never stops, is the area ever going to stop? No, we would see something that has infinite area in this situation. We can't deal with that. Okay. Now, the last one, you guys are going to hate this. We'll do tomorrow. So, good luck getting sleep tonight knowing there's another theorem floating around here. All right, later, Raiders.